Chapter 4, Section 2, Patterns and Linear Functions. So copy down the word example. The table shows the relationship between the number of photos, x, that you take and the amount of memory, y, in megabytes that's left on your camera's memory chip. They're asking if the relationship is a linear function. Describe the relationship using words, an equation, and a graph. So, we have the table here. The title is camera memory. Our x values are here, and our y values are here. They want to know first if the relationship is a linear function. Well, looking at the table, we can see that from 512 to 509, you subtract 3. From 509 to 506, you subtract 3. Each time you're subtracting 3 from the y values, you're adding 1 to the x values. 0, by the way, is the memory at 512 megabytes before any photos were taken. So this is the starting point. Now the independent variable x increases each by 1. Independent because the number of photos and the memory left depends on how many photos that were taken. So that makes the number of photos the independent, which is always x, and the memory left is the dependent, which is always y. So the dependent is decreasing by 3 every time that the x decreases by 1. So in words, the amount of memory left on the chip is 512, that's what we started with, minus the quantity 3 times the number of photos taken. Because 3 times for every 1, -3 over every 1, you started with 512, x is the number of photos. So you're subtracting 3 times the number of photos that were taken because you're subtracting 3 each time a photo is taken. So this is our equation that we get. Y equals 512 minus 3x. This is almost exactly like when we did equations, setting up an equation from a word problem, except now there's 2 variables. There's 2 unknowns, the number of photos and the memory that's left in megabytes. So here's the graph for the following question we just used. We use the table to make the graph. The points lie on a line, so the relationship between the photos taken and the amount of memory remaining is a linear function. So you can tell by graphing. Now notice this is on graph paper, so you should be graphing on graph paper. Here at the bottom, we have our x-axis. Here at the top, we have our y-axis. We're labeling our graph camera memory. Our y-axis is labeled memory in megabytes. Our x-axis is labeled number of photos. You must show what you're counting by. So here each line represents 1. So 0, 1, 2, 3, 4. On my y-axis, there's a break in the graph because I'm not counting every number in between. We're starting at 500 and then counting by 2s. But I have to show that I'm skipping 2, 4, 6, 8, and everything below up to 500, so that's why you show this break. Then we're counting by 2s each time. We plot our points. We can see that it's a linear function. It's decreasing, and we have our graph now representing the information that was shown to us in the table. Now let's look at the next example. So it's asking if the relationship in the table is a linear function, and to describe it using words, an equation, and a graph. Just for future reference, we're going to just tell whether or not it's a linear function. We're not going to graph this as well. So is the relationship on the table below a linear function? Well, when we look at the x values, we see that they're increasing by 1 each time. So the input, the x values, are increasing by 1 each time. The output are increasing by 2 each time. This is called a constant rate of change. Now, the rate of change here, when you add the same number every time, that number is called the common difference. And we're going to talk about this more in the future. But just to mention it now, when the x and the y both have a common difference, that means that the function is linear. So in other words, let's say that this last number here were 15. So the last number increased by 3. That would mean that it didn't have a common difference the entire time. It would not be linear. There would be one point that was away from the rest of the line. But when you're adding the same number to the y's and you're adding the same number to the x's, that means the y's have a common difference and the x's have a common difference. That means that it is a linear function. So looking at the following set of ordered pairs, I want you to take out a sheet of graph paper, label your axes, x and y, make sure there's arrows at the ends of them. This is on graph paper though. X and y. Make sure you either number your points when you plot them. So in other words, when you plot 0, 2, either number it 0, 2, or number your axes, label your interval as whatever you're counting by. So you need to have one or the other. Now when you plot these points, what do you notice about them? So take a minute to plot the points. You're going to notice that 2 of the points are vertically above one another. This is not a linear function at all, not possible. It's non-linear because you can't connect them into a straight line. And if we look, we're increasing here by 1, then we're increasing by 2, then we're increasing by -2. Whereas here, we're increasing by 2, then by 1, and then by 3. There's no common difference here. It's non-linear. Also, if we would have switched these so that it was 1, 4, 1, 8, 3, 5, there still wouldn't have been a pattern. But what else is different about this type of function? Well, by looking at the coordinates, we can see that there is an x value that repeats. Something cannot be a function if the x value repeats. If any one input, which is the x value, has more than one output, which is the y value, not only is it nonlinear, it is not a function. So no one x value can have more than one y value. We're going to see in the future, some of you may have heard already, seen it in the past, a function must pass the vertical line test. You have to be able to draw a line anywhere on the graph, a vertical line anywhere on the graph, and it should only hit one point of the function. Here you can see it hits 2 points, so that means it's not a function. Finally, we have our slope formula. So the slope formula is y2 minus y1 over x2 minus x1. So here we see our table. Well, just to rehash what we've been talking about, the rate of change here for y, each time we're increasing by 8. But then we see from 19 to 23, we're only increasing by 4. Well, let's look at the other side. The x values are increasing by 2, but then they're increasing by 1. Well, we want to see if there is a constant rate of change. And we can tell that we're increasing by 8 every time we're increasing by 2. Here, we're increasing by 4 when we increase the x values by half of that. So let's try to find the slope of this. Let's say that this is my x1, y1, and this is my x2, y2. So I'm going to plug in y2, which is 11, minus y1 over x2 minus x1. We get a slope of 8 over 2, which reduces to 4. Well, now let's try it with the last 2 points. So I'll make this x2, y2, and this x1, y1. This gives us 23 minus 19 over 5 minus 4, which gives us 4 over 1, which is just a slope of 4. Well, this is interesting because it's showing us that they have the same slope, which means this is a linear function. Now, a linear equation is written as y equals mx plus b, where b is the y-intercept. So the y-intercept means wherever it intersects the y-axis. So if we have our coordinate plane, wherever the line intersects the y-axis is the y-intercept. So it also means wherever x equals 0. So in this case, x is 0, y is 3. So our y-intercept is 3. Y and x stay the same, and the slope is what we just found, which was 4. This is written as a linear equation. In order to change it to a function, we're just going to write the function at x equals 4x plus 3. So they're written exactly the same way, but this is a function and this is an equation. F of x is the same thing as y. So on your graph, you would just label it as f of x instead of y. But make sure if they ask you to write the function, you write f of x, and if they ask you to write the equation, you write y equals.